about to start. How about you talk to me afterwards? Okay, people. So, assignment 5 due middle of next week. No new assessment comes out today. Hooray. Remember, some revision seminars next week. Do put in a request on the forum or by email if you've got something you want covered. You need to give me a little bit of time to write the questions and make the slides and so on. So get in sooner rather than later on that. And please, 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 if you haven't filled out a SETU, please do. Okay, so this is our very last seminar worth of content. And so we're basically going to be talking about 2 ways you can build spanning trees. So remember from last time, very important, a spanning tree is a tree that is a subgraph of some graph, so it's a spanning tree of a graph G, and it needs to be a subgraph of G, it needs to be a tree, and it needs to touch every vertex, right? So these are ways of building spanning trees. And so they say to search a graph G systematically, it helps to have a spanning tree. There's lots of reasons you might want a spanning tree. Remember, trees are sort of the minimum work you need to do to connect things. So a tree can sort of form a skeleton for something, and there's various uses for that. And of course, when we're doing this, it helps to think of, well, you can think of a couple of different situations. If you want to think in terms of practicalities, maybe you've been given a adjacency matrix of a graph which is, 10,000 vertices big, right? And so you don't have, and I mean 10,000 vertices is small if we're talking like the Facebook social network graph or, something like that, right? Could be much bigger. Might not be stored in an adjacency matrix in that case, but so you sort of can't get a picture of this graph in your head all at once. You can only sort of see it locally, right? When you're at a particular vertex, you can think, what's around me? But you can't get a global holistic picture of it necessarily, and maybe this sort of thing might be useful. Or if you want to think a bit more poetically, imagine you're exploring a network of caverns or something, right? And so you don't know what's going on except at places you've visited and seen and checked out, right? So those are the sorts of images to have in your head, perhaps. Okay, so we're going to learn about breadth-first search and about depth-first search. Breadth-first search is based on a data structure called a queue, right? Which probably many of you have seen, but very simple idea. Imagine you've got, say, a bookshelf or something. You put the books in at the left, and, well, in fact, we're going to say you put the books in at the right, and then you take them out from the left. But the important thing is that the first thing you put in is also the first thing to come out, and things queue up behind it, right? So let's imagine processing the letters of string with a queue. Basically, that means I'm going to run through them, taking some in and dropping some out of my queue, right? So first I'm going to take S into my queue, and because it's the only thing in my queue, it's the head of my queue. The head of my queue is the most important thing. It's the thing that is waiting to be served, right? And then maybe I'm going to take T into my queue as well. But it's queuing up behind S, right? I'm not going to do anything with it until I've dealt with S. It's just waiting. And maybe I'll take R into my queue. So now T and R are waiting behind S. And then maybe I deal with S in some way, right? So I do whatever I need to do with S. I've dealt with it, I've served it, I can drop it out of the queue, and that means everything moves left one click, and now T is at the head of my queue after having waited its turn. And now maybe I add I to my queue, and maybe then I deal with T, and so now R is at the head of my queue, right? Notice that things come to the head of the queue in the order we add them to the queue, right? Maybe I deal with R. Now I is the head of my queue. Now I add N to my queue. Now I deal with I. Now I add G to my queue. Now I deal with N, which is the head of my queue. Then G becomes the head of my queue, then I deal with it, right? Does that make some sense? So we're adding things on the right, we're dropping them out on the left, and the most important letter in our queue is the one that I am writing on the left here. Of course, it doesn't really matter how you represent these, but that is the head of the queue. Okay, so that's queues. Okay, so let's talk about breadth first ordering. So the one way to think of making a breadth first ordering or a breadth first spanning tree of a graph is that we're sort of dividing it into levels, right? We're picking a particular vertex to be a root, and then things that are distance 1, distance is the number of edges minimum I need to walk over to get there, away from the root will go on the first level, distance 2 will go on the second level, and so on. So that's the sort of thing this will create, right? Just a general idea to get what's going on here in your head. So, okay. So, and I guess broadly speaking, the idea behind breadth first search is we look close to our start, we look close to the beginning before we look at things that are further away, right? So we're going to, if we're walking into this imaginary cave network and A is the entrance, we want to look at the caverns that are close to the entrance before we go deep into the cave in any sense, right? Okay, so this is what we said about queues, right? So remember, things, the first thing that goes in is the first thing to come out, and this is going to be how we process the vertices when we do a breadth first search, right? So first we're going to put our root vertex in at the head of our queue, and then we're going to progressively add things that are next to our root vertex to our queue, and then we're going to use our queue as the order in which we keep exploring. So each time we look at whatever is at the head of our queue, we look at that vertex, we look at what's next to it, we add those new things to the back of the queue, and then we rinse and repeat, right? So, okay. And then we only take things out of the queue, we only remove our head vertex once we've fully explored from that vertex to everywhere else we can go, once we've added all the adjacent vertices to the tail of the queue. So let's see how that works in practice. So, what does this mean? I'm going to show you this, and then I'm going to show you an example, and then I'm going to show you this again. So we begin with T being the tree with just one vertex V0, which we have chosen to be the root of our spanning tree of this graph. And then, and so there's two bits to this algorithm, two things we're building. T is a tree, Q is a queue, right? Capital Q is a queue. And so we add V0, our root vertex, to our queue. And then, while this queue has stuff in it, we do the following. So we look at whatever vertex is at the head of our queue. So initially that's going to be the root vertex, but later on it might be something else. And then we look at the edges going out from that vertex. So we only have to look locally from that vertex. Now, if there's an edge that leads somewhere we have not been before, so leads somewhere to a vertex that is not in our tree, in that case, we add the edge and the vertex to our tree, but we also put that vertex in at the back of our queue, at the tail of our queue, right? And then once we've done that, for every edge that was adjacent to our vertex at the head of our queue, then we've explored everywhere we can from there, and we drop that vertex out of the queue. We're done with it now, right? So let's actually see that in practice. So this is an example the notes give. I'm going to give you a bunch of these examples. So let me say one thing first, which is that obviously when you do these algorithms, there's a bunch of arbitrary choice involved, right? So you can pick which vertices you go to first from a particular vertex. We're going to always, when we have an arbitrary choice between multiple vertices, we're going to follow alphabetical order, right, of these vertices that will, for us, always be A, B, C, D, E. And so that's the way to do it if you see it on a cheat sheet or indeed on an exam, for example. Okay, so how does this work? So because we're going in alphabetical order, we're going to pick A to be the root vertex, right? So A, our tree becomes just the vertex A, and our queue becomes just A. And now we look at the neighbours of A and we add any of them we haven't already seen, and we haven't seen anything at this point, to our queue. And because we're going in alphabetical order, the first one we're adding is B. So it gets added to the back of the queue, and we add the edge and the vertex to our tree, right? And then we think, have we explored everywhere from A? No, not yet, right? We've also got this edge to C, so we add that edge and the vertex to our tree, and we add C to the back of our queue. And now A is still at the head of the queue. We think, have we explored everywhere from A? Is there anywhere that we haven't seen? But we have seen both B and C. They're now in our queue. So we can say, okay, we've dealt with A. And so we drop it out of the queue to mean that it's now done, right? We've seen everything we can see from A. Okay, now our queue is BC. And so B is at the head of it. And so we do everything we just did from A, except now we're working from B, right? So we look from B and we say, where can I get to from B? And well, we can get to C, but we have already seen C, right? So we're not interested in that. But we can also get to D and E, and we're going in alphabetical order. So we look and we notice we can get to D, and that means we add that edge and that vertex, and we put D in the back of my queue. If you're using my silly exploring a network of caves or whatever example here, I imagine that these steps are all done while you're still in cave B, right? You're just shining your torch and you're saying, oh yeah, I can go there, I will go there later. It's on my list of places to go now, right? So you do that with D, and you do that with E, right? And so we add BD, we add D to our Q, we add BE, we add E to our Q, and now we think, okay, is there anywhere else I can go from B? No, so I drop it out. Is there anywhere else I can go from the next thing in my queue, which is C? No, because we've been everywhere. I drop it out. Is there anywhere else I can go from D? No, so I drop it out. Is there anywhere else I can go from E? No, so I drop it out. So this is sort of, these last steps might seem kind of pointless to you because you sort of know that this is your whole graph, but there's a couple of situations where they're less pointless, right? Or a couple of ways to think about why they're less pointless. The first is that sometimes you might be trying to find a spanning tree, well, sort of find a spanning tree in a disconnected graph, right? In which case you can't, obviously. What you will find is a spanning tree in a component of a disconnected graph. So maybe this is just a tiny little clump in a big 10,000 vertex graph, right? In which case these last steps are checking, is this really on its own, or can I get elsewhere, right? Or if you're, you know, exploring the caves or whatever, you need to go there and shine your light around to double check that there's nothing else you're missing, right? Same idea. Any questions on that? Yeah?
So we remove A only because there's nowhere else to go from A?
Only because there's nowhere else to go from A.
Keep on going from B, and if theoretically B were to run out of places to go before we hit E, then we would remove B as well and start from C?
Yes, absolutely. Yep, yep. So, yes. We only remove things once we have gone everywhere from them. Yep. Okay, so just to go back to the algorithm, so hopefully you sort of get it fully now you've seen it in action. Remember, we add a vertex, a root vertex to our queue, and then we look at our head vertex, we look at everywhere we can go from that vertex, one by one, in alphabetical order, we add those edges to the tree and those vertices to the back of our queue. And then once we've done that fully for a vertex, we drop it out from the head of the queue, and then we repeat the process at our new head of the queue, right? Remembering, of course, we only add things in, only add edges in when they're new places, right? Places we haven't seen before, because of course otherwise you'd make cycles, right? And we don't want to do that. Okay, so I mentioned this before, but if your graph G is not connected, then this will give a connected component of your graph, whichever component contains your root vertex. Right, so probably the way, really, the only sensible way to test a huge graph to see if it's connected, which is a really important thing to do potentially, is to start running either a breadth first or a depth first algorithm to find a spanning tree. If that spanning tree has 10,000 vertices and your graph has 10,000 vertices, then you know it's connected, right? If it has less than that, then you found a chunk, a piece in your graph which is not connected to the rest of it, right? So your graph is disconnected. Okay. And being able to recognize connectedness, for example, lets us recognize bridges, right? If you take away an edge and then you find your graph is disconnected, that's a bridge, right? Which is maybe giving you some insight into why that Fleury's algorithm, supposed improvement of the Euler-Trail algorithm is not so hot, right? You've got to do work, potentially, to recognize which edges are bridges. Questions? Okay, so one more breadth-first search thing. How would we construct a breadth-first spanning tree of this graph? So I think the way we would do that is like this, right? I think our breadth-first tree would look like this. Why would it look like this? Well, we start at A, and we think, where can I go from A? Only to B. B goes into the queue, AB goes into the tree. Now we've gone everywhere we can from A, so we drop it out. Where can I go from B? Well, I can go to C and D. So C goes into the queue, BC goes into the tree, D goes into the queue, BD goes into the tree. Now I have been everywhere I can from B, so I drop it out. C is up next. Where can I go from C? Well, I can go to B, but I've already been there, of course. I can go to E, so E is new. CE goes into the tree, E goes into the queue. Now I'm at C, I've been everywhere I can be from C. It drops out. I check at D, anywhere else I can go from D. Well, I can go to E, but I've already been there. It drops out. Can I go anywhere from E? No, and U, it drops out. Right, and then your algorithm's finished. Okay, so you do one. Tell me what I would get if I did a breadth-first search on this one. Take a little bit of time over this. How are we doing? Take a little bit longer. Okay. Okay, I think I agree with you. So, let's think about what would happen here. We start at A and we look around, right? We think, where can I get from A? And we can get to B and D and E. And in that alphabetical order, we would add those three edges to the tree and we would add them all to the queue, right? B, then D, then E. So our queue would be A, B, D, E, right? Then we've been everywhere we can from A, so it drops out. So where do we go next? The first place we added to the queue, which was B, right? So at the moment I've got these three edges, and now I'm exploring from B. Well, from B, the new places I can get are C and F, right? So I'm going to add this edge and this edge, right? And then I have, and C and F to my Q, and then I have been everywhere I can be from B, so that will drop out. Remember, my Q initially was A, B, D, E, so my next place to visit after B is D, right? It's next in my queue. So where can I get from D? Well, I've already been to C, so only place I can get is H. So I'm going to get this vertex. So A, B, D, E is next. Well, I can't get anywhere new from E because I've already been to F and H. So it's going to drop out. The next thing in my queue was C, and I'll get CG from there. Does that make some sense? So I think in the end you get this from A, you get this and this from B, you get this from D, and eventually this from C. So I think you wind up with this tree here. And notice that I'll talk more about this later, but a spanning tree, this is a really important property. A spanning tree that you build by depth first search has this property that every path in it from your root vertex to another vertex is one of the shortest paths you could possibly do in your graph. So for example, here, my path from A to G is length 1, 2, 3. Well, that's as short as I can do in this graph. Whereas here, for example, in D, my path from A to D is length 1, 2, 3, but actually I can get there in one step, which means this couldn't have been built by a breadth first search, right? Okay. First two are actually good visualizations, and other ones not so much. Okay. So, so that was part one. That was queues and breadth first search, right? So we're going to move on to depth first search, and depth first search is basically exactly the same algorithm, except that the data structure underpinning it is different, right? So instead of being a queue, it is now a stack. And a stack, remember I said a queue is like books on a bookcase. You put them in at the right and take them out on the left. A stack is like a stack of books on the floor, right? You put a book on top of the stack, then you can't get to the books underneath it until you've dealt with the book on the top of the stack. Right? So you put them down and pick them up from the same place. And for us, that's going to be the right-hand side. So if we were processing string with a stack, we might put S into our stack, and now we put T into our stack. But the big difference here is that as we put T into the stack, we change the top of the stack to T, right? The most important thing in our stack is now T. It's whatever we last put in. Then we put R in, and R's now our focus. It's now the most important thing. So even though S went in first, it's getting further and further away from being processed, right? Okay, maybe now we process R. So we've dealt with the thing at the top of our stack. Now the top of our stack is T again, right? And now we could add I to our stack, because we've dealt with R, remember? Now it's the top of our stack. Maybe we use it. Maybe we use T. Now we add N to our stack. whatever goes in last is the most important top of the stack, and that's what we eventually take off. Make sense? So in a sense, this would be much easier to visualize if I drew everything at 90 degrees, right? Then you really do have R sitting on T, sitting on S, and it's like a stack of books. You can't take things from underneath, you've got to take from the top, right? Okay. So, most important letter is now on the right, the top of the stack, the last thing that went in. Last in, first out. Okay, and now this depth first algorithm, it's worth noticing, is exactly the same algorithm as our breadth first algorithm, except where we have replaced queue with stack and head of the queue with top of the stack, right? But of course, this creates this totally profound difference, which is in a queue, we were being terribly systematic and saying, we'll explore from the first place we visited out of all the things. We were keeping this nice queue. We will now explore from the next thing in our queue, which was the first out of all the things in our queue that we visited. With a stack, you're doing the exact opposite. You're like, wherever I am, that's where I'm looking around from, right? So in my head, you know, the person using a breadth first search to explore the caverns is keeping a very careful map and very careful notes, and the person using a depth first search is just charging ahead with a torch or whatever, right? Okay. So, exactly the same. We start with just one vertex, our root vertex, we put it in the stack. Now, from the top of the stack, we add an edge to an adjacent vertex, if one exists, and then it becomes, we add it to our stack at the top. And that means effectively that we move there, right? Because now we're focusing from there, and we only remove something from the stack if we have explored everywhere we can from that. Okay. So let's do a depth first search. Here, I sort of think in some ways these are easier to imagine. I start at A, and I look around and I say I could go to B or C. Well, I'm going to go to B because it's first in the alphabet. And now I'm at B, right? B is the top of my stack. So now I'm looking around from B and I say, where can I go? Well, C, D, and E, but I'm going to go to C first because it's the first letter of the alphabet out of C, D, and E. So I go to it, and now C is the top of my stack. And then I think, where can I go from C that's new? Well, only E, right? I've already been to these places. So now I add E, CE, E's the top of my stack. Now where can I go? Oh, I can go to D. And so I add ED, D's the top of my stack. And now, can I go anywhere else from D? No. Can I go anywhere else from E? No. Can I go anywhere else from C? No. Can I go anywhere else from B? No. Can I go anywhere else from A? No. So that last bit, in this case, it was sort of boring, but notice that you're charging ahead and then effectively you're retracing your steps until the next place where you could branch off is the basic idea. So that's the algorithm again. Let's read this first. So to attempt to explain the joke, I guess, there are certain situations where you the things close to where you start are the most important, and as you get further away, those things are less important, and a depth-first search might take you right away from the zone of importance in that case. All right? Okay. So, let's see a slightly more interesting depth-first search then for this graph. This one will at least involve a little bit of backtracking. So, how would we do it? We start at A. We think, where can I go from A? Well, I can go to B, C, and D. I'm going to go to B because it's first in my alphabet. Now I'm at B, right? I've added this edge to my tree. I've added this vertex to the top of my stack. So B's now my focus. Where can I go from B? I can go to C or D. C's first in the alphabet. I'm going to add C to my stack and this edge to my tree. Now, where can I go from C? Well, nowhere new, right? I've already been to A or B, A and B. So I'm going to take C away from the top of my stack and basically effectively retrace my steps to B. Right? Now I'm looking from B again. Where can I go? Well, I've already been to A and C, but I haven't been to D. So I add that in. Now I'm at D. Where can I go? The only new place is E. I add that in. I'm at E, can't go anywhere. At D, can't go anywhere. At B, can't go anywhere. At A, can't go anywhere. Make sense? So in my head, this was someone running down here and down here, then thinking, oops, you know, dead end, can't go anywhere new, then retracing their steps to here, then running along here and down here, and then progressively retracing their steps, checking that they couldn't get anywhere else, right? Okay, so tell me, same graph, different search algorithm, what are you going to get? How are we doing? Another 30 seconds. Okay. I agree. So, YD. So, I think the way this goes is your stack starts as A. You think, where can I go? B, D, or E. But we add B because it's the first in the alphabet. Now B is the top of our stack. Where can I go? Well, C or F, but C because it's first in the alphabet. So we're going along here and up here. Where can I go? D or G, but D because it's first in the alphabet. I add this. Where can I go? H is the only new place, so I add that. Where can I go? G or E, I go to E. Where can I go from E? Only new place is F. Where can I go from F? Only new place is G. So here there was no backtracking at all, right? Which was why we got this path, oops, that was D, right? So this, I guess, gives you sort of some idea of one potential advantage of depth-first search in certain situations. If you want long paths, then depth-first search is much more likely to give you long paths. Sometimes that's a disadvantage, other times that's an advantage. Okay. So question 32.1 in the notes says, is this a queue or a stack? Who thinks it's a queue? Yeah, I agree. I think it's a queue because things are entering on the right but leaving on the left, right? A fell out here, whereas if this was a stack, the next, and we got rid of something, it would have to be C we got rid of, and it'd be AB. So, good. Yeah, in a stack, things that enter and leave in the same place. Okay, so very roughly speaking, remember, breadth-first search is the very careful person who is taking notes and drawing a careful map and always going out from the first place they visited out of all the places, right? Or the first place they detected, they looked at. Whereas depth-first search is the person madly charging ahead. Wherever they are at the moment, they're going somewhere from there, right? So go from the last place I visited, and that is precisely the difference between a queue and a stack, right? Stacks say whatever you did last is the most important thing. Queues say whatever you did first out of all this stuff is the most important thing. So, huge important property of spanning trees generated by breadth-first search is that every path from the root to another vertex is one of the shortest paths. And that's really, really useful sometimes. If, for example, you're looking at the graph of a social network or something, and you're trying to find, you know, you're playing 6 Degrees of Kevin Bacon or whatever, you're trying to find how many steps you are away from someone else, then you want to do a breadth-first search, right? Depth-first search isn't going to tell you anything, but breadth-first will. Okay, so very useful in analysing distances in networks. But on the other hand, well, if you want long paths, as we mentioned, or there are situations that are the opposite of the snake venom date, right, where the thing you're after is probably very far from where you started, right? So if this is a computer game where the most valuable treasure is all in the caverns that are far away from the start, then breadth-first search is potentially going to waste all your time in these low-value, easy caverns at the beginning, right? Whereas if you just dive in, you might get to, you know, maybe you miss the good stuff, but if you know it's far from where you started, better to take a guess than to spend all your time where you know it's potentially not, right? Okay, so that is all I've got for you in terms of content. So well done on getting through that. Next week, we'll be doing some revision. So requests definitely encouraged, but have a good weekend. Yeah.
You know where the ed is located in Moodle?
I don't think there is an ed for this subject.
Yeah. So I have to email you the requested subject that I need you to review for.
Sorry?
For the requested subject that I need, that you say you're gonna take requests from students.
Yeah. Oh, yeah. So either you can email me, but there's a thread on the exam discussion forum on Moodle. So sorry. That maybe that was what you were asking. What I should have said. One of the forums is exam discussion, and I set up a thread there for requests.
Oh, all right.
Yep.
Okay, thank you, sir.
Yep. Yeah.
For today's apply class, I couldn't understand the difference between a path and a matching.
Oh, okay. So they're sort of different. So like a path. So I should say matching we didn't cover except for this.
What about colors that aren't the rainbow spectrum?
Right. Just a bunch of
You can get all those by mixing the colors.
matching is sort of the opposite.
Well, technically, the primary colors, which is true red, white, and blue. So I only need the
Right. So it's graph,
like yellow, red.
where
I only need those three colors.
any vertex is only incident with one.
You might need it.
Right. So often matches are interesting because, like, if you, for example, let's say you've got, you know, people who want to adopt a dog, for instance, from the shelter over here, and dogs to be adopted here, and these are
He just looks at
the people who are prepared to adopt the various dogs. You want every person to adopt one dog. What you're looking for is a match. Right? You want to match up. Does that make sense? Yeah. Well, sort of. Yeah, parallel lines. Yeah, you know, no two touching, right? Which is sort of saying, you know, no two people are getting the same dog, or you know. Shortest path length from the root. Yeah. So for everything, you know that the path in the tree is one of the shortest ways. Not, you know, there might be others, but one of the shortest ways to get from the root to there. But of course, no guarantees between other two vertices, right? It's the roots, the special ones.
So that would be like the same as like what
Yeah, although isn't Dijkstra where you've got two vertices and yes, but if you pick the root and any other vertex, then yes, yeah. Yeah.
I've been hearing different things from different people.
Yeah.
Some people saying it's going to be in the on the exam, some people are saying no, so I just wanted to confirm that with you.
Okay, so on the exam, is exactly what you see on the practice exams, if you want to have a look at them.
Okay.
But it is a sheet with the formulas exactly from the useful formulas page.
Okay.
Right, not the useful notation, just the useful formulas.
So still the ones that are like at the end of the notes.
Yep,
Like
the
to
one,
formulas.
yeah, but
It's not every single one.
well, it is every single one from that one page at the end of the
Okay.
notes that's
Yeah.
headed up
Yep.
useful formulas.
Useful formulas,
And in fact, it's perhaps arguably slightly better on the exam because the logic laws are named, which they're not in the notes.
Okay.
So you've got all of that, but nothing from the useful notation page.
Right.
But then also remember you've got a page of double-sided A4 page of notes you're allowed to bring
Okay.
in. So
Yep.
you can do what you want with that one.
Thank you.
Yep. Also, just while I'm pointing you at things, there's a under scheduled final assessment on Moodle. There's also hints for exam preparation PDF. So read that. That's got a bit of stuff on that in it.
All right. Have a good weekend, sir.
You too.